Welcome friends. In the previous module, we discussed the graphical method for solving linear programming problem. In that method, we saw the solution set of a linear programming problem and we considered the vertices of the solution set and identified the optimal solution of the problem. In that case, the solution region actually it is called a convex set. Then in this module we are discussing what is a convex set and what is a convex function and what are the other related mathematical ideas behind the solution of a linear programming problem. First of all, we are going to discuss what is a convex set. Consider 2 points x1 and x2 on a space. x1 and x2 on a space. Then for a constant lambda, the point x equal to 1 minus lambda into x1 plus lambda into x2 for 0 less than or equal to lambda less than or equal to 1 is called the convex linear combination of the points x1 and x2. It is a point lying in the line segment joining the points x1 and x2. It is a point on the line segment joining x1 and x2. A set x belongs to K. A set K, the set is denoted by K, belongs to the Euclidean space of dimension n E n, is said to be convex if x1 x2 belongs to K, then x equal to lambda into or 1 minus lambda into x1 plus lambda into x2 also belongs to the set K. Then the set K is called a convex set. Let xi belongs to En and lambda I for I equal to 1 to etc. m be non-negative real numbers such that summation I from 1 to m lambda I equal to 1, then x equal to lambda x1 plus lambda x2 plus etc. lambda 1 x1 plus lambda 2 x2 etc. plus lambda m x m is called the convex linear combination of the points xi for I equal to 1 2 etc. m. Next, we are considering a problem. In this problem, we want to show that the set S equal to the set containing xy points such that x square plus y square less than or equal to 4 is a convex set. So, in solution we are considering the points x1 equal to x1 y1 and x2 equal to x2 y2 belongs to the set S. We want to prove the set S is a convex set. Here, since x1, that is x1, the point x1 ordered by x1 y1 belongs to the set S, x1 square plus y1 square is less than or equal to 4, and x2, that is the ordered by x2 y2 also belongs to the set S. Therefore, x2 square plus y2 square also less than or equal to 4. Now, consider the point Z, that is equal to the ordered pair Z1 Z2 be a convex linear combination of x1 and x2, such that z is equal to 1 minus lambda into x1 plus lambda into x2 for some 0 less than or equal to lambda less than or equal to 1. By the definition of convex set, when z is also belongs to S for all lambda such that 0 less than or equal to lambda less than or equal to 1, then we can consider the set S as a convex set. For that, we are trying to prove the set which is the convex linear combination of x1 and x2 also belongs to the set S. Set, we are saying the convex linear combination of x1 x2, that is set, where set is the ordered pair z1 z2 belongs to S if z1 square plus z2 square is also less than or equal to 4. So, here z is equal to, you can write it like z1 z2, that is equal to 1 minus lambda into x1. x1 is x1 ordered pair x1 y1 plus lambda into x2. x2 means ordered pair x2 y2. That is equal to 1 minus lambda into x1 plus lambda into x2. Then next point is 1 minus lambda by y1 plus lambda y2. This is z1 z2. Now, z is an element of S when, as we said, when z1 square plus z2 square less than or equal to 4, then we are saying z is also an element of S. Here z1 square plus z2 square, we can check what is happening for z1 square plus z2 square. Here z1 square plus z2 square is equal to, z1 is 1 minus lambda into x1 plus lambda into x2 the square plus, next is z2 square, that is 1 minus lambda into y1 plus lambda into y2 the square. This is z1 square plus z2 square. Now, here 1 minus, this is equal to 1 minus lambda the whole square into x1 square plus lambda square into x2 square plus lambda into 1 minus lambda into x1 into x2, then plus 1 minus lambda the whole square into y1 square plus lambda square into y2 square plus, sorry, 2 lambda, here also 2 lambda into 1 minus lambda into y1 y2. This is z1 square plus z2 square, that is equal to 1 minus lambda whole square, then x1 into x1 square plus y1 square, here 1 minus lambda whole square into y1 square, here 1 minus lambda whole square into x1 square, combining these two, 1 minus lambda whole square into x1 square plus y1 square, then plus lambda square into x2 square plus y2 square, lambda square into x2 square plus y2 square, then plus 2 lambda into 1 minus lambda into x1 x2 plus y1 y2. We are getting z1 square plus z2 square like this. That is less than or equal to 1 minus lambda the whole square into 4, because x1 square plus y1 square less than or equal to 4. So, we are substituting 4 instead of x1 square plus y1 square. So, the entire quantity is less than or equal to 1 minus lambda whole square into 4 plus, similarly the next term lambda square into, here also x2 square plus y2 square, but we know x2 square plus z2 is x2, that is x2 y2 is a point on the space on the set S, that is x2 square plus y2 square less than or equal to 4. So, lambda square into 4 plus 2 lambda into 1 minus lambda into x1 x2 plus y1 y2. So, that is less than or equal to, that means 4 into 1 minus lambda the whole square plus 4 lambda square plus 2 lambda into 1 minus lambda into x1 x2 plus y1 y2. We are getting it like this. Here consider x1 y1 minus x2 x1 y2 minus x2 y1 the whole square. Consider the term x1 y2 minus x2 y1 the whole square, that is equal to x1 square y2 square plus x2 square y1 square minus 2 into x1 y2 into x2 y1. We are getting like this. Since it is a perfect square, this is greater than or equal to 0. This implies x1 square y2 square plus x2 square, here it is y1, x2 square y1 square is greater than or equal to 2 into x1 y2 into x2 y1, 2 into x1 y2 x2 y1, or 2 into x1 x2 y1 y2, x1 x2 y1 y2. That means 2 x1 x2 y1 y2 is less than or equal to, that is 2 into x1 x2 y1 y2 is less than or equal to x1 square y2 square plus x2 square into y1 square. Okay. This implies x1 square x2 square, we are adding some terms to both the sides, x1 square x2 square plus y1 square into y2 square plus 2 into x1 x2 y1 y2, that is less than or equal to, actually in this side we added x1 square x2 square plus y1 square y2 square. To compensate this, in the next side also we are adding x1 square x2 square plus y1 square y2 square plus there it is x1 square y2 square plus x2 square y1 square. But now here this side is x1 square x2 square plus y1 square y2 square plus 2 x1 x2 y1 y2 can be written as x1 x2 plus y1 y2 the whole square, x1 x2 plus y1 y2 whole square, that is less than or equal to, now the next side can be written as x1 square plus y1 square plus here it is x1 square plus y1 square into x2 square plus y2 square, that is x1 square x2 square, that is here, x1 square y2 square, that is here, y1 square x2 square, that is here, then y1 square y1 square x2 square, that is here, then y1 square y2 square, that is here. So, that is less than or equal to x1 square plus y1 square into x2 square plus y2 square. This implies x1 x2 plus y1 y2 the whole square less than or equal to. That side there is x1 square plus x2 y1 square plus into x2 square plus y2 square, but we know this x1 square plus y1 square, that is the ordered, that is the point x1, that is ordered where x1 y1. Since it is in, it belongs to the set S, x1 square plus y1 square is less than or equal to 4. So, here instead of this we can substitute 4, then there is no change in the inequality, into x2 square plus y2 square, that is also less than or equal to 4. So, into 4. This implies x1 x2 plus y1 by 2 is less than or equal to square root of 4 into 4, that is less than or equal to 4. So, we can make use of this result to calculation of z1 square plus z2 square. So, here we are getting this is less than or equal to 4 into 1 minus lambda whole square plus 4 into lambda square plus 2 lambda into 1 minus lambda. Here we have x1 x2 plus y1 by 2, but now we proved x1 x2 plus y1 y2 is less than or equal to 4. So, here if we are substituting instead of this 4, there is no change in the inequality. So, we are getting z1 square plus z2 square less than or equal to 4 into 1 minus lambda the whole square plus 4 into lambda square plus 2 into lambda into 1 minus lambda, that means less than or equal to 4 into 1 minus lambda the whole square plus, okay, 4 can be taken out, then 1 minus lambda whole square plus lambda square plus 2 into 4 is taken out, then 2 lambda into 1 minus lambda. So, we got it as z1 square plus z2 square less than or equal to 4 into 1 minus lambda whole square plus lambda square plus 2 lambda into 1 minus lambda. That means, this is less than or equal to, here 1 minus lambda whole square plus lambda square plus 2 lambda into 1 minus lambda. What is happening here? 1 minus lambda the whole square, that is equal to 1 plus lambda square minus 2 lambda, then plus lambda square, then plus 2 into lambda minus 2 into lambda square, 2 into lambda minus 2 into lambda square. That is equal to lambda square plus lambda square 2 lambda square and minus 2 lambda square, that is cancelled, then minus 2 lambda plus lambda, that is cancelled. So, this entire quantity is becoming 1. This implies z1 square plus z2 square less than or equal to 4 into 1, that is z1 square plus z2 square less than or equal to 4. That is our required result. Here if x1 is a point that is ordered by x1 y1, then x1 square plus y1 square less than or equal to 4. So, because that belongs to the set S, and x2 the ordered pair x2 y2 we considered it like that. So, since it belongs to S, x2 square plus y2 square less than or equal to 4. Finally, we considered the point Z, which is Z1 Z2 ordered pair Z1 Z2. That is a convex linear combination of x1 x2. Finally, we got Z1 square plus Z2 square is also less than or equal to lambda for all lambda where 0 less than or equal to lambda less than or equal to 1. This gives the convex linear combination of x1 x2, that is set also belongs to S. Hence, by the definition of convex set, the set S is convex. So, for a set K to be convex, it is necessary and sufficient that every convex linear combination of points in K belongs to K. In next problem, we are considering intersection of two convex sets, and we want to show that intersection of two convex sets is a convex set. For that, we are considering two convex sets S1 and S2. S1 and S2 are considered convex. Assume x1 equal to ordered pair x1 y1 and x2 equal to ordered pair x2 y2 are 2 points. They belongs to x1 and x2 belongs to S1 intersection S2. That is the intersection of the two considered convex sets S1 and x2. If x1 and x2 belongs to S1 intersection S2, we can consider or we can conclude x1 belongs to x1 and x2 belongs to S1 and x1 and x2 belongs to S2, then only x1 and x2 can be in S1 intersection S2. If x1 and x2 belongs to S1, S1 is a convex set, then the convex linear combination of these x1 and x2 is also belongs to S1. That means 1 minus lambda into x1 plus lambda into x2 also belongs to S1. Similarly, next x1 and x2 belongs to S1 because x1 and x2 belongs to x1 intersection S2. If x1 and x2 belongs to the convex set S2, then the convex linear combination 1 minus lambda into x1 plus lambda into x2 also belongs to S2. That means 1 minus lambda into x1 plus lambda into x2 belongs to S1 and 1 minus lambda into x1 plus lambda into x2 belongs to S2. This implies 1 minus lambda into x1 plus lambda into x2 belongs to S1 intersection S2 also. So, here we considered x1 and x2 belongs to S1 intersection S2, where S1 intersection S2 is the intersection of two convex sets. Then the convex linear combination of these x1 and x2 also belongs to S1 intersection S2. Therefore, if S1 and S2 are two convex sets, their intersection S1 intersection S2 is also convex. That means the intersection of two convex sets is a convex set. Next, the convex hull of a set S is the intersection of all convex sets of which S is a subset. Convex hull of S is denoted by the symbol S. For example, consider this type of set. Let this be a set S. Then the convex hull of the set S, convex hull of the region S is the intersection of all convex sets of which S is a subset. You can consider here this set. When we are considering this circle, then this circle is a convex set, because for any point, any 2 points we are considering inside of the circle, the convex linear combination, that means straight line joining that 2 points also belongs to this particular set. But actually in our case, the given set S is not a convex set, because when we are considering 2 points, 1 point here and 1 point here, when we are joining these 2 points or we are considering convex linear combination of these 2 points, we are getting many points outside the set S. That means all convex linear combination of x1 and x2 for all lambda, it is not again belongs to S. So, S is not a convex. But as before, this circle is a convex, and the set S is inside of the circle. Then next we can consider some more smaller circle. Then this circle is also a convex set which also contains S. Similarly, the intersection of these two, that means the inside circle, that contains this convex set, that contains the set S. Similarly, we are considering all possible convex sets which contains this set S, and we are considering intersection of all such convex sets. Finally, we are getting a shape like this. This is the intersection of all convex sets where S is a subset. So, this shape, that is the convex hull of the given set S. A convex set is its own convex hull. If this is a set, this is like a convex set. This convex hull of this set is itself. A convex set is its own convex hull. Next, we are considering the vertices or extreme points of a convex set. A point x on a convex set K, let be convex set is K, is an extreme point, the point is x, is an extreme point or vertex of the set K, convex set K, if it is not possible, to find 2 points x1, x2 such that x equal to lambda into or 1 minus lambda into x equal to 1 minus lambda into x1 plus lambda into x2 for 0 less than lambda less than 1. If x equal to 1 minus lambda into x1 plus lambda into x2 for lambda where 0 less than lambda less than 1, then x is a point on the line joining x1 x2, x is a point on the line joining x1 x2. Somewhere we can consider a convex set like this. These are the vertices of this convex set. Then these points, the speciality of these points are, these points cannot be expressed as the convex linear combination of 2 points of the set, let it be K. This point cannot be expressed as the convex linear combination of 2 points of this particular set K for some lambda where lambda is between 0 and 1. If point x1 is here and x2 is here, and if a point x can be expressed as 1 minus lambda into x1 plus lambda into x2 for some lambda between 0 and 1, definitely that point is nothing, that point is somewhere on the line joining of x1 and x2. So, if this is an extreme one, it is not possible to write this point x, let it be x, as the linear combination of any 2 points x1 and x2 of this particular convex set for some lambda where lambda is between 0 and 1. Then convex polyhedron. The set of all convex combinations of a finite number of points xi, set of all convex linear combinations for I equal to 1 to etc. m, is the convex polyhedron spanned by these points. The convex polyhedron is a convex set. Next is hyperplanes, half spaces and polytopes. Let x belongs to En, where some constant c not equal to 0. It is a constant, a row vector, row n vector and alpha belongs to R, we define number 1 a hyperplane as x such that Cx equal to alpha, it is called a hyperplane, and 2 a closed half space as x such that Cx less than or equal to alpha, is a closed half space. An open half space as x such that Cx is less than alpha, this is an open half space. The intersection of a finite number of closed half spaces is called polytope. Is called polytope, that is the intersection of a finite number of closed half spaces. The half spaces are unbounded convex sets, since intersection of convex sets is again convex. Polytope is a closed convex set. Now, we are going to discuss some useful results. The first result is a set K to be convex, it is necessary and sufficient that every convex linear combination of points in K belongs to K. that is we can write as a set K. To be convex, it is necessary and sufficient that every convex linear combination of points in K belongs to K. Result 2. If a set K is non-empty, closed convex set and bounded from below or above, then it has at least one vertex. If a set K is non-empty, closed convex set and bounded from below or above, then it has at least one vertex. The third result, every point of a convex set K is a convex linear combination of its vertices. That is another result. Every point of a convex set K is a convex linear combination of its vertices. Next, we are moving to familiarize with the convex functions. Convex functions. Recall that a subset K belongs to En is said to be a convex if for any 2 points x1, x2 belongs to K, the point x equal to 1 minus lambda into x1 plus lambda into x2 also belongs to K. For lambda where 0 less than or equal to lambda less than or equal to 1. Next, if K belongs let K belongs to the Euclidean n space En, where K is a convex set, then a function f of x is said to be convex. The function f of x is said to be convex function if for any 2 points x1 and x2 belongs to K, for any 2 point x1, x2 belongs to K, f of x is less than or equal to 1 minus lambda into the function value at x1 plus lambda into the function value at x2. For 0 less than or equal to lambda less than or equal to 1, and for every x for every x that is equal to 1 minus lambda into x1 plus lambda into x2. Then the function f of x is called a convex function. Now, what is a concave function? Concave function. The function is concave if the inequality sign is reversed, or if the concave function, if the inequality sign is reversed, that means f of x greater than or equal to 1 minus lambda into f of x1 plus lambda into f of x2, or if f of x is convex, minus of f of x is a concave function. Then we can picturize a convex function like this. Let this is the point x1, this is point x2 somewhere here, and this is the line joining x1 x2, that means convex linear combination of x1 x somewhere here x. Now, a function is like this. Here function value at x1, that is here, this is the function value at x1, and this is function f of x, and function value at x2, that is here, f of x2, here it is f of x1. Then function value at x, that is here, this is f of x, but 1 minus lambda into f of x1 plus lambda into f of x1 is somewhere here. So, here f of x is less than 1 minus lambda into f of x1 plus lambda into f of x2. Since f of x is less than 1 minus lambda into f of x1 plus lambda into f of x2, the function f of x is considered as a convex function. It is a geometrical interpretation of a convex function. Notice that x1 and x2 are any 2 points and x is such that x equal to 1 minus lambda into x1 plus lambda into x2 for some lambda such that 0 less than or equal to lambda less than or equal to 1. Next we can consider a problem. Show that the function f of x that is equal to 3x square, that is equal to f of x is equal to 3x square over the real line is a convex function. So, for that we are considering the points x1, x2 belongs to R1. Let x equal to, x is a point that is a convex linear combination of these x1, x2. That means that is a point on the line joining x1, x2. X equal to 1 minus lambda into x1 plus lambda into x2, that is considered as x. Now, f of x is equal to f of 1 minus lambda into x1 plus lambda into x2, that is equal to 3 into 1 minus lambda into x1 plus lambda into x2 the square, because our f of x is 3x square. Now, f of x1 is 3x1 square and f of x2 is 3x2 square. Our problem is to prove that f of x that is equal to 3x square is a convex set. Sorry, f of x is a convex function. So, to prove this function f of x is a convex function, as a definition by the above definition, we want to prove f of x is less than or equal to f of x1, sorry, 1 minus lambda into f of x1 plus lambda into f of x2. So, here f of x so here 3 into or f of x minus 1 minus lambda into f of x1 plus lambda into f of x2. If this is less than or equal to 0, we can say the function f of x is a convex function. So, here f of x minus 1 minus lambda into f of x1 plus lambda into f of x2 is 3 into 1 minus lambda into x1 plus lambda into x2 the whole square minus 1 minus lambda into 3x1 square plus lambda into 3x2 square. So, this is here it is 3 can be taken out, 3 into then 1 minus lambda into x1, expand 1 minus lambda whole square into x1 square plus lambda square into x2 square plus 2 lambda into 1 minus lambda into x1 into x2 minus 1 minus lambda into x1 square minus lambda into x2 square. So, that is equal to one minus lambda whole square and 1 minus here that is equal to 3 into lambda 1 minus lambda minus 1, that is 3 into lambda minus 1 into x1 square, then plus lambda into lambda 3 is outside, lambda into lambda minus 1 into x2 square, then minus 2 x1 x2 into lambda into lambda minus 1. You can write it like this. This implies, or that is equal to 3 into lambda minus 1, then here inside of the, when we are taking out lambda into lambda minus 1, the remaining terms are x1 square plus x2 square minus 2x1 x2. That is 3 into lambda minus 1 into x1 minus x2 the whole square. Here 3 into lambda minus 1 into x1 minus x2 the whole square is 3 lambda into lambda minus 1 is greater than or equal to 0, and x1 minus x2 the whole square is also greater than or equal to 0. Since 0 less than or equal to lambda less than or equal to, when we are considering, that is equal to 3 into lambda minus 1 into x1 minus x2 whole square, but since it is a perfect square x1 minus x2 whole square, this quantity is greater than or equal to 0, and lambda, that is 0 less than or equal to lambda less than or equal to 1. But this lambda minus 1, since lambda is in between 0 and 1, this lambda minus 1 is less than or equal to 0. Because of this lambda minus 1 is less than or equal to 0, the entire quantity 3 lambda into lambda minus 1 into x1 minus 2 x2 the whole square is less than or equal to 0. That means we are getting this f of x minus 1 minus lambda into f of x1 plus lambda into f of x2 is less than or equal to 0. That is, the function f of x, that is 3x square over R1 is a convex function. Now, we are familiarizing with quadratic forms. Let x belongs to En. A homogeneous expression of the second degree of the form f of x is equal to C11 x1 square plus C22 x2 square etc. plus Cnn xn square plus C12 x1 plus next is C12 x1 x2 plus C13 x1 x3 plus etc., where Cij belongs to R for I equal for I comma j equal to 1 to etc. up to n is called a quadratic form in the n variables x1, x2, etc., xn. If we substitute aii for cii and aji plus aij for cij, such that aij equal to aji, that is equal to 1 by 2 into cij for I not equal to j, the quadratic form can be put as f of x is equal to a11 x1 square plus a22 x2 square plus etc. plus ann xn square plus a12 x1 x2 plus a21 x2 x1 plus etc. That is equal to summation over I from 1 to n, again summation over j from 1 to n, then aij xi xj, that can be put as x dash a x, where this X and A are matrices, where X is a column vector, that is X is equal to x1, x2, etc., xn dash, and A is the real symmetric matrix containing the values like this. A is a real symmetry matrix where A is contains the point A11, then A12, etc., A1n, then A22, sorry, A21, A22, etc., A2n, and then last row, that is AN1, AN2, etc., ANN is a real symmetric matrix. Then as a definition we can say a quadratic form, it is called a quadratic form x dash Ax, a quadratic form x dash Ax is said to be positive definite if x dash Ax greater than 0 for all x not equal to 0, positive definite. It is said to be positive semi definite if positive semi definite if x dash Ax greater than or equal to 0 for all x not equal to 0, and there is at least one non-zero vector for which x dash Ax equal to 0. Negative definite and negative semi definite forms are defined by reversing the inequality signs in the above definition. That is x dash Ax less than 0, that is negative definite, and x dash X less than or equal to 0, negative semi definite. And some theorems are here based on this quadratic form. Let x belongs to En and f of x, a function which is in quadratic form x dash Ax, be a quadratic form if x dash Ax is positive semi definite, then the function f of x is a convex function. That is x dash Ax is a positive semi definite, then this function f of x is a convex function. You can prove it like this. Let x1, x2 be any 2 points in En, and x is equal to convex linear combination of these x1, x2, 1 minus lambda x1 plus lambda into x2. Notice that 1 minus lambda into f of x1 plus lambda into f of x2, 1 minus lambda into f of x1 plus lambda into f of x2, that is equal to 1 minus lambda into f of x1 is x1 dash Ax1 plus lambda into f of x2 is x2 dash Ax2. Our aim is to prove f of x is a convex function if x dash Ax is positive semi definite. A function f of x is convex function, if f of x is less than or equal to 1 minus lambda into f of x1 plus lambda into f of x2 for some lambda 0 less than or equal to lambda less than or equal to 1, then this function f of x is a convex function. Or 1 minus lambda into f of x1 plus lambda into f of x2 minus f of x is greater than or equal to 0, then the function f of x is a convex function. Here we are trying to find what is a 1 minus lambda into f of x1 plus lambda into f of x2 minus f of x in our form. This is equal to, we know 1 minus lambda into f of x1 plus lambda into f of x2 is 1 minus lambda into x1 dash Ax1 plus lambda into x2 dash Ax2 minus f of x is x dash Ax, but our x is 1 minus lambda into x1 plus lambda into x2. So, this is equal to 1 minus lambda into x1 dash Ax1 plus lambda into x2 dash Ax2 minus x, that is 1 minus lambda into x1 plus lambda into x2 dash A into 1 minus lambda into x1 plus lambda into x2. Okay, that is equal to 1 minus lambda into x1 dash a x1 plus lambda into x2 dash a x2, then minus of this 1 minus lambda into x1 plus 1 minus lambda into x1 plus lambda into x2 dash into a into 1 minus lambda x1 plus lambda x2. Okay, we can rewrite it as lambda into 1 minus lambda into x1 dash a x1 plus x2 dash a x2 minus 2 x1 dash a x2. That is equal to lambda into 1 minus lambda into x1 minus x2 dash a into x1 minus x2. That is greater than or equal to 0, because 0 less than or equal to lambda less than or equal to 1 and x1 minus x2 is any vector in En. Therefore, we are getting f of x is less than or equal to, or this 1 minus lambda into f of x1 plus lambda into f of x2 minus f of x is 1 minus lambda into f of x1 plus lambda into f of x2 minus f of x is greater than or equal to 0. This gives the function f of x is a convex function. The aim of the next theorem is to establish the fact that if f of x is a convex set, convex function, then any relative minimum point will be a global minimum. That is theorem is stated like this. Let k belongs to En be a convex set and f of x is a convex function. If x0 is a point of relative minimum, it is also a global minimum. Also, if this minimum is attained at more than one point, then the minimum is attained at the convex linear combination of all such points. We can prove it as, let f of x have a relative minimum at x0. Let x1 belongs to k. Then for any delta greater than 0, it is possible to choose lambda, such that 0 less than lambda less than 1, such that there exists a x that is 1 minus lambda into x1 plus lambda into 1 minus lambda into x0, and x1 are our point, x0 plus lambda into x1 lying in the neighborhood of x0 is somewhere here, x0 lying in the neighborhood of x0 somewhere here, x equal to 1 minus lambda into x0 plus lambda into x1 lying in the neighborhood of x0. By the definition of relative minimum, with x in the neighborhood, f of x0 less than or equal to f of x. That is f of x0, less than or equal to f of lambda into x0 plus 1 minus lambda into or lambda into x0 plus 1. If you are considering it, is like this, x is equal to lambda into x0 plus 1 minus lambda into x1. Then f of x0 less than or equal to f of x, that means f of x0 less than or equal to lambda into x0 plus 1 minus lambda into x1. That is less than or equal to lambda into f of x0 plus 1 minus lambda into f of x 1. This implies 1 minus lambda into f of x 0 is less than or equal to 1 minus lambda into f of x 1. This implies f of x 0 that is less than or equal to f of x 1. That means f of x 0 is a global minimum. To prove the second part, let y 0 be another point where the minimum is attained. Then f of x 0 equal to f of y 0. Take x equal to lambda into x 0 plus 1 minus lambda into y 0. Then f of x 0 less than or equal to f of lambda into x 0 plus 1 minus lambda into y 0. That is less than or equal to lambda into f of x 0 plus 1 minus lambda into f of y 0. That is less than or equal to lambda into f of x 0 plus 1 minus lambda into f of x 0, because f of y 0 is equal to f of x 0, that is equal to, we are getting it is equal to f of x 0. This implies f of x 0 is equal to f of lambda into x 0 plus 1 minus lambda into y 0 for all lambda where 0 less than lambda less than 1. This means that minimum is attained at all convex linear combination of x 0 and y 0. This proves the theorem. Let us conclude this session here. Hope you all enjoyed this session. See you next time. Goodbye.